in which flux qubits could be made reproducibly with very long coherence times. And so over the years, what happened was that flux qubits now and then had long coherence times, but those results were not reproduced, and it took a long time to understand the reasons for this. It has to do with specifics of the coherence that were understood only recently, and in particular quasi-particles in superconductors. Yeah, so you are close to that limit in optimized devices. So yeah, and this is a recent development. So, and now once you have that, so flux qubits are basically as good as transmons, with the difference that in order to have that, you have to stay at this sweet spot here, where the transition frequency is insensitive in first order to apply magnetic fields. And this looks like a serious restriction, depending on, if you think about doing computation. Actually, that's what I was planning to cover in the second part of my talk. But the point is that even with that restriction, you can actually do universal quantum computing. So that is interesting thing to consider. Yeah.
Yeah. Is it possible to show the full Hamiltonian for the flux qubit before you go to this small region?
So your question is whether you can solve?
No. I like to know what is the full Hamiltonian.
Oh yeah.
Circuit.
I should have added a slide on that. In fact, I don't know if I can write. I asked if I could write on something. Well, it's actually okay. Let me in fact. Okay, it really is not that complicated. Actually, all that goes into it is terms of this type. So you have, instead of this. So this phase variable here can be seen as can be looked at as being the phase difference between the phases between the condensates on the two sides of the Josephson junction. In the transmon, you only have one of this because it is a system with a single junction. In a flux qubit, you have three of these phases, and the three phases are constrained. So their sum is constrained by the magnetic flux applied to the loop. So you have a sum of three cosines with a constraint in the phase, basically. So it's as simple as that. And one key point is that constraint in the phase is actually what leads to this potential becoming anharmonic. Okay. So any other questions? Yeah.
Is there an interaction between the quantum particles and the qubits that might cause a bit flip? Why not?
Yeah. And this was only. This was only understood properly in recent years, actually. And what was really interesting is that when I think about quasi-particles, there was in a sort of naive way, but that was really, I think, how most people thought about it at that time. When you think about quasi-particles, you think about charges, and you think about charges not really being relevant for a flux type of qubit. But we understood recently that actually quasi-particles are even more damaging for flux qubits than they are for transmons. And there are complications with microscopic details such as superconducting gas being uneven and so on. And this led to lots of irreproducibility between different experiments done in different labs on different devices and so on. So quasi-particles can be quite damaging, and the recent optimized design of flux qubits actually address this issue, so that's why we can have long fluxation times. All right, so let me see. I guess I just wanna say a bit about, if there are no other questions, say a bit about the second topic. So I just want to talk about quantum control of a single qubit, which is a trivial topic, but I think in the case of superconducting qubits, comes with an interesting twist. So I don't know. Well, I guess probably everybody here is in the field of quantum information, or maybe most of you are. This is a way to represent a state in typical in quantum information, where any superposition is written as in terms of these coefficients, alpha 0 and alpha 1 of the two energy eigenstates. So any state can be parameterized with these two angle parameters, the angles theta and the angle phi. So the angle theta is about the relative populations of the ground and excited state, and the angle phi represents the relative phase of these two states. So these two parameters can be written as a vector of norm 1 with these coefficients here, and it is usually represented in terms of these blocks here, where this vector pointing from the origin to the surface of the sphere is is basically a geometrical representation of this angle theta with the z-axis and the angle phi made with the projection made with the x-axis. So this is the Bloch sphere representation of the state. So now when you take the Schrodinger equation for a single qubit, you can write it in the following way. So the Hamiltonian can be written as a sum of the three Pauli matrices with some coefficients which depend on the value of the Hamiltonian. These coefficients are omega x, omega y, and omega z. And qubit dynamics can be seen as simply as the precession of the polarization vector that I showed earlier, p, around this omega frequency, which is basically the parameterization of the Hamiltonian. So the standard way to do qubit control is illustrated here. So in the left frame, the typical control Hamiltonian is one in which the qubit has an energy level splitting delta, and then there is a transverse control term. So this term is off diagonal in the qubit energy eigenbasis. This control term is taken to be just a cosine with an amplitude envelope and the phase. So you basically turn on a pulse, you keep it running for a while, and then you turn it off. You can control both the amplitude and the phase in this pulse. And it's simple to understand the dynamics in the rotating frame, where this Hamiltonian can be written in the following form. So the rotating frame is a frame in which you are undoing the evolution of the qubit due to this Z field. So if you think of just the Z field, the qubit will simply precess around that Z field. So if you are going to a frame where this evolution is being removed, the Hamiltonian has this expression over here. And there is a standard approximation being done, the rotating wave approximation, which brings the Hamiltonian to this form here. So, and this rotating wave approximation simply considers that high frequency components in this Hamiltonian can be disregarded, because these high frequency components average out basically during the qubit evolution. So in the rotating frame, the Hamiltonian is written in this way. It has two components, sigma x and sigma y, and these two components can be controlled by the amplitude and the phase of this signal you apply. So for a flux qubit, this would be an applied magnetic field. So now, if you think about an AMO context, everything is done in a similar way, and usually think of a regime where the amplitude of this control pulse A is much smaller than the energy level splitting of the qubit delta. So this is really a limitation of laser powers, for example, for atomic physics, where it would be really hard to get anywhere close to this regime. Now in superconducting qubits, it's really easy to get access to that regime, and this is also the case in some other implementations, in quantum dots as well. For example, you can reach this regime where the driving amplitude is larger than the qubit transition frequency, and we are interested to see what happens in that case. So if you take this amplitude to be, well, before saying that, let me say that if you think about the rotating frame, the dynamics can be simply seen as precession around an axis defined by these two components, a cosine of phi and a sine of phi, related to the driving field. If you go to to a regime where A is comparable to delta, then the dynamics when A is not too large still looks like a rotation of the Bloch sphere around this fictitious magnetic field, if you want. But you start to see some departure from that, you start to see some additional high frequency oscillations. And if you look at this at first, it doesn't look like there is much of a structure to these oscillations. But we did discover that there is actually a coherent framework to look at these dynamics, and one which actually gives us some useful insight on coherence. On gate fidelity. And this framework is Fouquet theory, as I'm going to explain in just a bit. So now let me just say that there was lots of work done prior to our work on strong driving of superconducting qubits. As I said, experimentally, it's a relatively accessible regime in this field. Some of these dynamics was looked at from the perspective of Landau-Zener tunneling. So if you think about the two qubit levels that I showed earlier, you can think about this as being magnetic flux. one thinks about how this strong driving field simply takes you across this minimum gap region over here, and at each crossing you have a probability for the state to go from one energy branch to the other energy branch. This is a coherent process, and as a result of many of these processes, you can reach a certain steady state. So this was looked at in particular in this experiment in 2005. There are also experiments which in this regime of strong driving looked at multi-photon excitation. So these are processes in which you can excite a qubit with transition omega by subharmonics of that signal. So this was done in a few experiments. But we were interested in probing the dynamics of strong driving with a particular focus on keeping a coherent dynamics and also achieving the highest fidelity gates. And we looked in detail at the role of pulse shaping and adiabaticity, and the use of the Fouquet picture in quantum control. So this is a schematic of the experiment. This is how an actual flux qubit looks like. So what you see is a scanning electron microscope picture of the device. So it's a superconducting loop with a few of these tunnel junctions. So these overlap areas here are tunnel junctions. Here shown schematically is a representation experiment where this flux qubit is placed inside the superconducting resonator. The resonator here is used for quantum state readouts. So if you probe microwave transmission through this resonator, you can look at the signal here, which tells you something about the state of the qubit. So you can measure the state of the qubit in the energy eigenbasis. And then here we send a microwave pulse. So this is an AC signal with a frequency nearly resonant or nearly resonant with the qubit transition frequency, and with an amplitude and duration chosen such that you implement certain operations on the qubit. So, one a bit of more of a technical detail, but really relevant in this experiment, is that the typical way of generating these microwave pulses involves high stability frequency source and then microwave modulators. But in this experiment, we generated these control pulses using direct digital synthesis, which is something, again, very unique to the field of superconducting qubits. So when you think about doing this in the context of atomic physics, you think about taking a laser, shining a laser on your atom. So that's a coherent signal generated in a particular way. Now, superconducting qubits have transitions in the microwave regime, and at these frequencies, you can actually generate signals point by point using high-speed electronics equipment. And this is what you can see here. So this waveform is fully digitally synthesized, and this is really very useful in this type of experiment that I'm going to show you, where we want to have very detailed control over the amplitude and phase of these pulses. So when you look at how the qubit population changes as a function of the pulse duration, so again, this is the pulse is shown here. So in this case, we look at the pulse with very sharp rise and fall edges. So again, the amplitude, the product of this amplitude and the duration of the pulse should control the rotation angle of the state. So this will tell you how many oscillations you are undergoing between the ground and the excited state of the qubit. And these are the standard Rabi oscillations. So if you do this experiment with a control amplitude, which is only 4% of the qubit transition frequency delta, when you look at the state of the qubit, the average state of the qubit as a function of the duration of the pulse, which is on this axis here, so this is in nanoseconds, you see some clear oscillations where the population of the state 1 goes between 0 and 1. So these are periodic oscillations of the state of the qubit, and this is really your standard textbook quantum control. But when we are making this driving amplitude higher, for example, when we go to close to half of the transition frequency of the qubit, we see again these oscillations. They are much faster, so you can see the time scale is significantly different here. So they become about 1 nanosecond periodicity. And besides this, you also start to see some additional structure here. So these oscillations start to have other frequency components. And when you increase the driving amplitude even higher, then these oscillations start to become really scrambled. But this is not really random. There is actually structure in here. And you can see this by taking a Fourier transform of this probability of the qubit as a function of time, which shows a single peak for the low driving regime, and then a couple of peaks as you go higher and higher in amplitude. And if we take oscillations like this and we show the Fourier spectrum as a function of this driving amplitude, we get a color plot that looks like this. So what you're seeing here, so this axis is the driving strength, so this is how strong the pulses are. This axis is the frequency in the Fourier transform we take to analyze the oscillation. And the color scale here is the amplitude of different components in this oscillation spectrum. As you can see, this is a relatively regular pattern, and it turns out that the proper framework to understand this is Fouquet theory, which describes this in general terms the solutions of the Schrödinger equation with the time periodic Hamiltonian. So our qubit is driven with a periodic signal, and the state at any point should be or can be written as a superposition of two Fouquet states. These Fouquet states are the product of a wave function which is periodic in time, with the period being the periodicity of the drive, and a phase factor with an energy-like coefficient C alpha called the quasi-energy. And for those of you familiar with solid-state physics, there is an analogy here between these states in time and Bloch states for electrons in a solid, and it's the same type of underlying symmetry that gives this property to the solution of the Schrödinger equation. So when you look at these quasi-energies, they actually change with the driving amplitude as shown here. And the reason why we see this oscillation spectrum, it has to do with the fact that since the wave function at any time can be written as the superposition of two Fouquet states, the probability to find the qubit in state 1 is given by the scalar product. And when you take the scalar product, you can see that there are some interference factors which involve the difference in quasi-energy between the two Fouquet states, but also all the harmonics of the driving signal omega. And this, when we compare the results, the experimental results with numerical simulations, we see this really clear agreement between the data, which are points, and these quasi-energy branches. So this provides a direct measurement of these quasi-energies for the driven system. And maybe the last, so I think I'm going to stop pretty soon. The last thing I want to bring up, just to get to the point where I thought this was useful for quantum computing as well, is that we found, and in fact we didn't really expect this before doing the experiment, we found that there is actually a very interesting dependence of this oscillatory pattern on the rise and fall time of the pulses. So again, the pulses sent to the qubit is shown here. So this is the amplitude of the applied magnetic flux. So this pulse has an amplitude AM, and it's patterned in this way. So there is a flat top here of duration TP, and there is a rise and fall time TR and TF respectively. So when you do this, when you look at the oscillation between the ground and the excited state with long rise and fall times, we see actually a very clean Rabi-like oscillation between the two states of the qubit. And this is despite the fact that the driving amplitude is more than half the qubit transition frequency, where normally you wouldn't expect the rotating wave approximation to work anymore. But then as you are making this rise and fall time shorter and shorter, these oscillations start to have some irregularities, and eventually they become really scrambled. And we found that this has a nice interpretation in terms of adiabaticity in the Fouquet picture. So when you think about turning on and off this driving amplitude, what you are doing effectively is you are changing the instantaneous eigenstates, these quasi-energy states of the driven system. And if you do this in a smooth way, then actually all that you are doing is you are picking up a phase factor for these quasi-energy states. So in terms of the Bloch representation that I showed earlier, the state of the qubit starts here at the North Pole, so this is the ground state. This state can be written as a superposition of the two Fouquet quasi-energy states. And on the Bloch sphere, this state would just precess around this fictitious field here, around this vector, which is set by the difference between the two quasi-energies. So if you're just turning on this quasi-energy difference slowly and then turn it down slowly, all you are getting is a smooth oscillation in time with a total phase which depends on the integral of this quasi-energy in time. And this leads to this surprising feature that in fact dynamics you get is pretty much like Rabi dynamics, although you are driving the system extremely strongly. And we learned from this that you can actually apply this to implementation of very fast single qubit gates. So if you do this ramp up and ramp down fast, but not too fast, and using another trick based on interference at these stages, so you can be non-adiabatic but use a favorable interference condition, you can actually do extremely fast single qubit gates. And let me just show you the final results. So we had a superconducting qubit with the transition frequency, it's not written here, the transition frequency was 1.7 gigahertz. We could do Rabi oscillations with a driving amplitude of 0.46 gigahertz, and we could attain extremely high fidelity over 3 nines if we shape these pulses properly. And we could do this over a time which was only 0.48 nanoseconds. So this is basically just a couple of oscillations long. It really is sort of unthinkable in the mindset of NMR, where we think about this as being really long pulses. But by really getting a hold of this Floquet physics, you can really shape these pulses in a way that gives you very high fidelity. And I would say it's both a curiosity in a way, just it's a regime that normally you cannot attain in other fields, and we've been looking at this in quite some detail. There was a lot of theoretical work in AMO, but not really amenable to a kind of clear experimental demonstration. Yeah, we learned a lot about single qubit gates, so they can really be made extremely fast, and fast gates means high fidelity because you don't have to compete with the coherence induced by the environment. And we are still thinking about whether some of this can be applied to high fidelities for 2 qubit gates and so on. So yeah.
Why I'm surprised that you see the other states here. You are driving a lot. I understand that you have like an important anharmonicity, but it should show up at some point.
Oh yeah, at some point, yeah. This is a very good point. So in this case, this qubit had a very high anharmonicity. So the third state, the second excited state, was very far away. We couldn't even see it, but we think it was at least 10 gigahertz away or so. So we are not close enough to see a transition into that state.
So have multiple photon excitation and all this.
Yeah, but they become significant enough at larger power. So that's beyond this point where the transition amplitude is equal to the qubit transition frequency. Yeah, so I think I will, thanks. And I think I want to leave things here, but I'm happy to take more questions or talk to you later. Okay, so. Yeah.
One question. In the diagram where you show the whole setup, including the readout,
Yeah.
can you go back to that diagram and explain us, are those signals all on, or they are on and off?
Oh yeah, so the question is, I guess, how do you run this experiment? So this is done by repeating periodically a procedure where you start with first of all, you wait for some time, you allow the qubit to relax to the ground state. So that's a way to prepare the qubit in a pure state. You can do other things, there are more sophisticated procedures, but that's easy enough, and it's still standard in most experiments. So you wait to let the qubit relax. That waiting time has to be a few times t1, so typically it can be anywhere between tens to hundreds of microseconds. Then you apply this control pulse. This pulse is typically nanoseconds to microseconds long.
It's a shape.
It's a shape pulse in general, yeah. And then you do state readout, which requires applying another microwave pulse which is resonant with the cavity.
These two needs to be synchronized.
They have to be synchronized, yeah. Yeah, so this requires triggering system and so on, because even propagation across your setup can damage this time alignment. So these details have to be sorted out. Yeah.
So if flux qubits are reproducibly long from
I think so. I think at least it should be looked at very thoroughly and analyzed with all the experimental details included. So one key point is that when you get this really very high coherence flux qubits, the anharmonicity also goes down, but it still is much higher than the transmon. So there is a trade-off there. So you have much more anharmonicity, but not as much as you have more anharmonicity than in transmons, but it's not really a two-level system. So it's about as coherent, but there is some overhead in operation. So there is more biasing and so on. And another key point is that to benefit the maximum coherence of flux qubits, you have to keep them at the sweet spot. And that means that you need to figure out a way to do multi-qubit gates with all the qubits kept fixed in frequency, and that comes with some challenges. It's actually a problem we worked on recently.
But the overhead in control is huge. Huh?
You mean?
Overhead in control, like in the control line that you need to add is important as far as.
You mean when you compare flux qubits and transmon? Well, I mean, not really. So when it comes to microwave signals, it's comparable. Maybe.
No, but the DC to tune the thing at the sweet spot. This is.
Well, yeah. So, but it really is a matter of sort of putting things in perspective. I would say. I mean, it is so. So with transmons, you typically have a tuning magnetic flux as well. There are versions of transmon circuits explored at IBM in particular, where the transmons basically are fixed in frequency and they have fixed interactions, so that requires no flux tuning. But that comes with a problem with very slow gates. So again, there's a bunch of trade-offs, and my opinion is that not all of this has been considered, and I think it should be considered in the light of these new developments. I mean, basically it's a huge design space that is not really being looked at properly. And I guess for good reason, but yeah.
So what's the state of the art? I remember, I guess for many years people have been looking at arrays of flux qubits to try to understand collective phenomena. So if you want to use flux qubits as some kind of simplified simulator for collective phenomena, not doing things like annealing,
Yeah.
just sort of understand other many-body physics. Is there a possibility of making arrays to do that?
Well, yeah, and actually there were a few recent experiments done in Japan at NEC and in Germany in Alexei Ustinov's group where they look at this. So the problem is you still need exquisite control to make qubits identical, for example. And it depends on the way you implement them. I think the way that was chosen in those experiments was not really such that it was a very robust process against fabrication errors. And this means that you end up with qubits that are all different from each other. And this is actually a general problem with superconducting circuits. So this is really a big obstacle against simulation type experiments, namely that you deal with systems that are sort of spread out, which is something you have in atomic physics as well, because of, well, atoms are the same, but because of external fields and so on. But in superconducting qubits, in general, this problem gets amplified. And I think there's always this dilemma. So if you want to develop a quantum simulator and you're really expecting this to provide some insight into physics, then you're doing this because the physics you want to explore is very complex to start with, right? So you want to understand something new, but then how do you factor in disorder? And that's always, to me, a very tricky thing to think about. So, all right.
Okay.
Let's give our speaker a hand. Thanks again.